Yeah, good day everyone. So we want to look at in the previous video I did show you how we can do the analysis, as in the calculation part of a transistor amplifier design using the popular potential divider method. So we have been able to find the value of R1, R2 and RE in the previous video, so which is titled the transistor amplifier design. So in this video we'll just implement what we have the values we have calculated, then we experiment. We try to put in some input signals and see whether we're able to get a gain of 4 as we have anticipated from our design, because the design basis for the amplifier we did in the previous video was based on the fact that we want a gain of 4. So we use that 4 as the basic value for our design. So we want to actually implement that. If you could remember very well, we did say that our R1 is 39 kilo ohms, our R2 is 10 kilo ohms, and our RE is 680 ohms. So that is what we have implemented on the screen. If you can see well, this is what we have just implemented on the screen. So we want to experiment this. Now. So let's start now. I think we are all used to the very component that we can see on the screen. Now these two guys is just probe. It's just generator mode. You go to generator mode, you pick a DC to assign the DC value of 9 volts. When you drop it here, you connect it to this base terminal, to the collector terminal here. Then you go there and pick sine. This one we model our signal generator or a function generator in the case of a physical laboratory environment. So this is like a signal generator. So what we do now is we try to assign value. We want to put a value of 0.1 volts amplitude, 0.1 volt AC audio signal. So let's see whether we have. Okay, I've set this one to 9 volt already. So let's try to see what the waveform. Now I put this oscilloscope to be able to measure the input voltage, that is the input signal, the signal that is not boosted, then the output signal that is coming from this amplifier. Remember, we take our output from the collector and the emitter. So because in a simulation environment, oscilloscope is assumed to be naturally grounded, so that's why you are only picking one terminal from the collector. So the ground is a virtual ground. So oscilloscope pick a virtual ground, just need one terminal. But in the case of a physical lab, you need to find a ground of the circuit and put the ground terminal of the oscilloscope. So let's look at the waveform and see how we can calculate the input voltage and the output voltage. So let's take one shot of this waveform. Then now remember what we said. The green, we connect the input to the green colored signal. Then we connect our output to the yellow colored signal. So that is, let's first measure the input signal, which is color green. So let's measure it. Now if you look at the waveform, you see there is a 0.5 peak. If you take your cursor here, if you measure between this point, between this line to the peak is a half, because the complete box is a 1. So which means it is divided into 2, which is half. So then you go and check the setting, the volt per division setting of this particular waveform is set at 0.2 volt. So which means every division represents 0.2, and we have half of a division, which means it's going to be 0.5 multiplied by 0.2. So if we pick our calculator, 0.5 multiplied by 0.2, that will give us 0.1. So which means the signal we put in is 0.1, just as we set You know 0.1 is what we set from the signal generator. So let's take a, okay, I have prepared this observation table. The input signal is 0.1. So let's check the output signal. Our output signal, you carry your cursor as well. Let's measure this. Let's try to make this signal to appear. Okay, this input signal is if you see that this thing has covered two boxes, so which means each half of the waveform is 1. So 1 multiplied by 0. Okay, let me make this one to be 0.2 as well. Okay, let me make it to be 0.2 so that both the voltage, both the input and the output are set at the same value. So when you look at it, this one is now set at how many boxes? 1, 2, 3, 4. That's 4 boxes. So which means each half of the cycle is 2 boxes. 2 boxes multiplied by 0.2, because each box represents 0.2, and we have 2 of such boxes. So you count 0.2 multiplied by 2. So that will give us 0.4. So our output is 0.4. So we fed in 0.1 and we got 0.4. So our output is 0.4. So let's feed another signal again. Let's feed in another signal. Stop the simulation. Go and set another value here. Double click. Let's set 0.2. At 0.2 volts. Let's check our waveform. Let's simulate it. Then take one shot. Let's take one shot. So let's move this this oscilloscope to cover one. So if you are looking at this place, you see that from here to here, from the peak to the peak, that's 2 boxes altogether for the input signal. 2 boxes multiplied by 0. That is, each one of them is 1. I mean, each half is 1 box. So 1 box multiplied by 0.2. 1 multiplied by 0.2. That will give you 0.2. So which confirms our input voltage of 0.2. So the output voltage, let's count the output voltage. Let's try to get, okay, let me make it here. So let's count how many boxes is covered. 1, 2, 3, 4, 5, 6, 7, 8 boxes. So which means each half cycle is 4 boxes. So 4 multiplied by 0.2. 4 multiplied by 0.2. That will give us 0.8. So it means our outputs of this transistor amplifier is 0.8. So the output is 0.8. Okay, so let's go and change the signal again. Stop the simulation. Double click. So let's change it to 0.3. Let's change the waveform to 0.3. So let's run the simulation. 0.3, take one shot. Okay, let's separate the waveform. Okay, so let's measure this. Let's try to get complete. Okay, so from here to here, so how many boxes? 1, 2, 3. 3 boxes. So which means each half cycle is 1.5. So 1.5 multiplied by 0.2. 1.5 multiplied by 0.2. So that will give us 0.3. So which actually confirm what we have set. So the input voltage we set is 0.3. So let's check our output voltage, our output signal. So let's check. Let me try to make this thing rest on this waveform board, or this line. So let's count from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 boxes is covered. 12, which if the whole cycle covers 12 boxes, which means each half cycle covers 6 boxes. So 6 multiplied by 0.2. 6 multiplied by 0.2. That will give you 1.2. So our output is 1.2. So let's go. Let's run 1 or 2 more before we stop. So let's stop this simulation and put a signal of around let's say 0.4 volt. 0.4 volt. let's put a signal of 0.4 volts and run our simulation. Let's take one shot. So this is a, let me try to separate the signal. Let's measure the input. Let's measure the input voltage first. The input voltage first. So this is how many? 1, 2, 3, 4. 4 boxes. So which means each half cycle is 2 boxes. 2 boxes multiplied by 0.2. 2 boxes multiplied by 0.2. 2 multiplied by 0.2. That will give us 0.4. So which actually confirmed the value we have put, 0.4. So the next one is to measure the output waveform. So let me take this one off so that I can bring this one to the first screen. So let me bring this one to the first screen. So let's count how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So which means each box is 8. 8 multiplied by 0.2. 8 multiplied by 0.2. 8 multiplied by 0.2. Sorry, there's a mistake. It's a mistake. 8 multiplied by 0.2. That will give us 1.6. So 1.6 is our output signal. 1.6. Then let's do that of 5. Then we stop the experiment and confirm our gain. So let's stop the simulation. Let's put this at 0.5. 0.5. So let's measure, run the simulation, take one shot of the waveform. Let's take this output out first. Let's measure our input waveform. So if I put it here, the output, so the output, let's measure it, the inputs rather. So let's count 1, 2, 3, 4, 5. 5. So which means each box is 2.5, right? If the whole cycle is 5, then each box is 2. Each half cycle is 2.5. 2.5 multiplied by 0.2. So that gives us 0.5, which actually agree with what we said, 0.5. Then let's measure our output finally. So let me take off this green so we can see. Let's take off this green. So let me bring up this. So since this one is becoming too big, what we can do is to change the, let's alter the time per division of the volt per division of this one. Now we have changed it to 0.5 per division. So let's try to measure it. So let's count how many. 1, 2, 3, 4, 5, 6, 7, 8. So 8 divisions. So which means each half cycle is 4 divisions. So 4 multiplied by 0.5. 4 multiplied by 0.5. That will give us 2 volts. So let's write 2 volt here. 2 volt. So if you want to calculate the gain, you know gain is a output voltage gain. Let's quickly gain, which is equal to, our gain is equal to output voltage, which is output voltage over input voltage, which is this divided by this. So let's bring it down. So you see that, okay, this one we did not, so which means our gain is 2 divided by 0.5, 2 divided by 0.5 is 4. So why is this one not? Let's try to C7. Okay, this is C7. Let me alter this one. This is C7. C7. This one is let me just C7. C7 divided by B8. This is C7. This is B7. C7 divided by B7. It's just, you can use calculator to do this, but I just want to use to calculate the Excel. But we've seen that so far we have gotten our, okay, I think it has worked now. So we have gotten our gain to be 4. 4 is the gain. So what is the gain of this one? It's just to draw it here. So the gain is 4. So which means we have been able to design an amplifier with a gain of 4. So that is how we design transistor amplifier. You see how we began the operation by calculating the different parameters from R1, R2 and R3. So that is how we run a transistor amplifier. Thank you very much for watching. Please do well to subscribe to this YouTube channel for up-to-date videos on electrical, electronics and other aspects of engineering. I still remain myself, Engineer Clement. So please recommend this video if you like it to your friends and to your classmates, your colleagues. And if you have any comments, please kindly do well to reach out to me through comment section. Thank you very much. Bye for now.